Hello, I'm Lindsay Clemens from the University of Idaho, and I'm here to talk with you today about measuring ocean acidification. So, when we think of the ocean, about the glorious sights it has to offer, one of the first things we think about are coral reefs. Coral reefs are definitely spectacular. They provide nutrition and protection for millions of species of fish around the globe. However, in recent years, there have been lots of catastrophic events. Around one-fifth of the world's population of corals have died, and about 60% are in imminent danger of doing the same. Now, some of these reasons have to do with the rising ocean temperature. However, ocean acidification is a major part as well of what's happening to this marine ecosystem. So what is ocean acidification? So ocean acidification is, as the name suggests, when the ocean pH goes down. In recent years, well, from the industrial evolution, pre-industrial evolution, the pH was around 8.179. However, in present day, it's gone down to 8.069. And this doesn't seem like a very large difference, but that is actually a 28.8 increase in H plus concentration. Now, here is the mechanism for how it goes. So you have the carbon dioxide in the atmosphere mixing with seawater, and this results in carbonic acid. From there, some of the protons can dissociate, and it can become free hydrogen ions and bicarbonate, or it can also go all the way down, dissociate with both of them, and become a carbonate ion. Now, why is ocean acidification important? So we've already touched on one of the reasons why, but coral reefs aren't just there to look pretty. Fish provide 16% of the world's protein, and fish they live a lot. A lot of them live in the coral reefs themselves. And that's not all of the reason why ocean acidification is very dangerous for fish and other life forms. As you can see from this shot of shells, you go from a really healthy looking shell to really opaque, and then it just dissolves. And this is what happens with creatures that use calcium carbonate in their shells, is that the bicarbonate and carbonate balance shown here, it gets disrupted, and there's much less carbonate in the water. And so because of that, it thermodynamically pulls the carbonate from the shells, and then they just dissolve, which is, of course, very bad news for anybody who uses calcium carbonate, such as corals, mollusks, snails. Now, the real question is, what can we do about it? And for us as scientists, the first thing we think about is, how can we quantify what's happening? How can we see how the pH is changing, how much, and where it's most affected around the globe? From here, we'll talk about the spectrophotometric pH system. And the spectrophotometric pH system is a system by which we can find the pH relatively quickly and relatively cheaply. So here, what happens is we have seawater, and we have an indicator dye that goes through a pump into a mixer. And the indicator dye, what it does is it mixes with the seawater, and after it mixes, it changes color. And that color will be detected from the absorption cell by the photodetector when it's hit with the light source. And it will measure the absorption. And the instrument control and data acquisition is controlled by the same main system. And it also computes the pH from the absorption that it measures. Now, why spectrophotometric pH is a better system than any others that are commonly used, like the potentiometric diode that we use, is precision and accuracy, but a lot of the reason is precision. Because it's been speculated and estimated that pH in the oceans changes around 0.002 pH units per year. And so the precision for the systems that we use has to be greater than 0.002 pH units. And so here is a graph, here's a table that we can see with all of the different systems that people presented data with. So for group A, in the top here, it's automated shipboard pH systems. So it is automated, but it has a person aboard the ship. So it's not completely autonomous like we would prefer. So you can see here precision. The first one and the last one are the precision we want. The middle two are not. But if we look at the automated in situ pH systems, these are ones completely by themselves. No humans with them for a while unless they come back and check on them. You can see that the precision is much better among these systems. Why the spectrophotometric pH system is so much more precise than the potentiometric system and other systems is because it is not prone to drift. It does not have to be calibrated. In the beginning, it's calibrated, but it doesn't have to be recalibrated. It essentially stays calibrated throughout the whole range of your use of it. Now, for applications and future work. So the reason why this very precise method is so useful is because we really want to check how the pH changes in places that also don't change very much. And so there are definitely places on the globe where it changes more and places where it changes less. And so you need to have precise equipment in order to see how it changes in places that aren't as prone to absorbing CO2, such as places that have warmer climates, as gases don't dissolve in warm liquids as well as it does in cold liquids. And however, even though the spectrophotometric pH system is very good, what it isn't good at is how big it is. And so what we want to do is to scale it down into this microfluidic pH system. And so it works much the same way. It has the spectrometer and it has an absorption cell, an LED light that it uses in order to calculate the absorption and thus the pH of the sample. And so in the future, the size is really what we want to pare down. And with this, we'll be able to check pH around the globe. We'll be able to set up more stations for less cost. And it will be a lot more rigorous understanding of how the pH is changing in the globe today. And with a better understanding, we can figure out ways to help the most affected areas. Thank you. If you have any questions, feel free to ask them.